So thank you very much for the invitation to all to the organizers, and also I appreciate that you stay here, although it is a little bit late. So on behalf of the name of Stefan, I send all the greetings to all of the persons on this room that knows him. So I'm at the moment a postdoc at the University of Kassel, and today I will speak about quantum friction near non-reciprocal media and chiral media. So this is the outline of my talk today, so only I will give you a very brief motivation because in the previous talks, the introductions have been very good exposed. And the introduction, the formalisms that we employ, and I will provide you some preliminary results about the frequency shifts, the decay rates on this moving atom for these two kinds of media. And finally, some conclusions. So the motivation mainly comes because in my PhD I focused on these topological insulators, on these topological materials, but mainly at the last part it came this article where they found that the quantum friction could be increased for these two orders of magnitude in two-dimensional topological materials. That's very important because since quantum friction was predicted theoretically, the effects are quite small. And also at the beginning of the last year, people that were studying this kind of nanochannels in carbon, they found that quantum friction could be the responsible mechanism that explains this weird effect that they found. So I'm also, and Stefan I would agree with me, but that we are also from the team Francesco, that we also regard Casimir force and Casimir-Polder as macroscopic interactions between macroscopic bodies. So Professor Karsten plotted in previous here the van der Waals force. Then you could imagine this in this degree of complexity. The Casimir force is between two macroscopic bodies. Then if you put one instead of the macroscopic body as an atom, then you will have the Casimir-Polder force. But our contribution to this series of complexity would be if this atom can move, then you will obtain the quantum friction that I will study in this presentation. So the two ingredients of this talk are quantum friction and the non-reciprocal media and also the chiral media. So first of all, what is quantum friction? So it's only an atom that is very close to the interface between a bilayer system. For instance, I will regard one of them as vacuum and the other it could be the non-reciprocal or the chiral media. And the atom moves parallel or even perpendicular to the interface. But in this case, I will focus only in the perpendicular case. So it was predicted by Pendry in this year. And the other ingredient for this talk is this kind of materials. Non-reciprocal medium is very easy to explain. It's materials that break time reversal symmetry. Until this point in this workshop, we have been studying only materials that respect this fundamental symmetry. But for this case, what does that mean? It means very basically that if you have one interface and you put the source in one of the parts, it means that if you are here, you can see at the other side, you will very briefly, if I see you, you can see me. And in the other side, if you can see me, I can see you. But that's reciprocity. In a non-reciprocal way is that I see you, but you cannot see me. So the physics is not more invariant under this time reversal symmetry. For instance, or just to fix ideas, here are the constitutive relationships for the easiest material, which is the non-reciprocal plate. Very important is that these constitutive relationships, you can see that both the electric and the magnetic fields are mixed. This is for a non-reciprocal media, but here is the ones related to the non-reciprocal, to the chiral medium. You can see that there are a lot of analogies between of them, but one has this, the imaginary part. And one of them, so the chiral, which is here, respect time reversal symmetry and the others no. So we will play with them. So the formalisms, we employ macroscopic QED, which comes from this expression, which basically connects the sources through the Green's tensors, and you obtain the response. Jn is the noise current density, and in the basic macroscopic QED, again, the Green's tensor respects a time reversal symmetry or the Lorentz reciprocity principle. Then the question would be, how could we adapt these formalisms to these new kind of materials, so the non-reciprocal ones? To that aim, we only employ Ohm's law. So we have, again, the noise currents, and through the electric field with this convolution through the conductivity tensor. In this way, because the Green's tensor is the most important object for these formalisms, it should satisfy a concrete modification to the Helmholtz equation, which is here this term in green. So then we quantize this, the theory through this through the noise current density as it is shown here, and this R is only square root of the conductivity tensor. Also, we impose that our operators satisfy the fluctuation dissipation theorem, and you can write it also for the electric fluctuations. At this point, it could be quite clear that there is no significant difference between these cases and the reciprocal case, but the difference comes from this modification of the imaginary part of the Green's tensor. You can see that if these two, that the operation of the transposed one are equals, then this will cancel, and then you recover the reciprocal case. Because we have already added some salt or some pepper to these formalisms, and it is a little bit more complicated in comparison with the reciprocity case, we would only focus for that time for temperature equals 0 in order to see what is happening with these modifications to the phenomena that we are going to study. So, because we are studying an atom, the fields, we also need to regard the atom field Hamiltonian. Here is the atom Hamiltonian, which is expressed in terms of the energy basis through the flip operators, the field Hamiltonian, which is quite known for you. And we write the atom field interaction in this way. So here you see, this is the dipole interaction, but because these new materials couples also the magnetic and the electric field, we need to take into account the Röntgen interaction. So let's move on. So then the recipe told us that we have to solve the Heisenberg equations for the operators in the non-relativistic velocities. We approximate also for Born-Oppenheimer approximation, and then we obtain F, and then through F we obtain E and B. Finally, we also need to solve the internal atomic dynamics of described by the flip operators. And we will assume a weak atom field coupling, and then at the end of this step, we will apply the Markov approximation. So the idea could probably be to obtain the force, as you can, we have been seeing all the day, but Stefan and collaborators in this paper proposed that it's quite difficult to measure forces, as we have already seen in experimental talks, and therefore I have a lot of respect for that. But to overcome that problem on how to measure forces, the idea would be to provide, instead of that, a spectroscopical quantities such as the decay rates and the shields. So in this philosophy, and focusing only on the ground state, we are able to obtain the frequency shift and the decay rate as I show here. So it can be split in two terms. The static term, let's say, which is these two are only Casimir-Polder, and these two are explicitly velocity-dependent terms. These terms can be through contour techniques split in the resonant and non-resonant contributions, and again, because all these expressions, which are quite long, depend on this new imaginary part. When you impose again that this Green's tensor satisfies again the reciprocity principle, you recover the standard expressions for the reciprocal media. Then let's put the feet on the ground and not be so abstract. So let's put some concrete ideas and some concrete media. So this is the situation. Let's put vacuum in the upper layer and the lower layer and the non-reciprocal medium. So fortunately, again, the Green's tensor, this is the easiest case, and it is already given, the Green's tensor here. And for this interface, there are two extra Fresnel coefficients. That means that the polarizations are now coupled. So you have to consider these two extra terms. I put here, these are not the most general expressions. These are only for the non-retarded regime, which we are going to study, or I will present here. And this capital delta, this Greek letter, it takes this form for the topological insulators, and alpha is the hyperfine, the fine structure constant. So all the time reversal symmetry breaking is inside this parameter. So then I apologize if there are a lot of formulas, but in the general case, considering an arbitrary dipole with complex components and also regarding only epsilon and mu as real parameters, we found the following results for the non-retarded limit for the frequency shift in the non-retarded regime. So this is the resonant component for only the Casimir-Polder quantities. So that means only for the atom that is static without the dependency of the velocity. So in green, you can see how the Fresnel coefficients enter into play here. And in blue, you can see that here only the moduli of the dipoles play here. So that means that explicitly here, it does not matter the polarization that you are taking into account. But for this term, which it comes from the from the coupling that we have from the electric and the magnetic field, you have this B, which is this explicit thing, and it seems strange, but when you look at the literature, this is a geometric magnetic field that is quite studied from the chiral physics, let's say. Then let's move on with the velocity explicitly dependent term. This term, which is this one, again, this term is only for the SS and the p peak polarizations. But importantly is this term, again, it comes from the crossed coupling, and this RNK is this one. This one is, again, probably could be strange, but again, after looking at the chiral things, this is called the chiral optical strength rotatory thing. This thing encodes how the magnetic moment and the electric moment of a certain molecule couples. But for this case, it's very important to think that we are only regarding a general electric dipole. Where does the magnetic dipole comes from? That comes because the atom is moving, it has a velocity, and then it induces an effective magnetic dipole. So that's the reason. And here in red, I highlight because this is, I put explicitly a 0, but we have, Stefan and I found some problems when we regard instead of only the parallel motion, when you regard the perpendicular one, these terms are not falling out when you are far away from the surface. They are still constant, they are spurious terms, and we do not know what is the problem. We are quite sure that the problems come because we are not able to sweep, or we are not taking it for this case correctly the limits. I mean that Markov probably is failing at this point. This is for the frequency shifts, and then for the decay rates, again for the same situation. Again here, for this contribution, it does not matter the polarization, and also for this one. So here there are no cross terms. That means that this could be, that comes explicitly only for the, from the contributions for probably like a perfectly conducting mirror, because there are no crossed terms. But interestingly, for the velocity dependent term, it's the opposite situation. The main contributions comes explicitly from the crossed terms. And again, we found this problem, and we are trying to solve it. So limited cases, again, here it could be two of them. If we send the crossed terms to equal 1, this term survives, and also if we send at the same time the SS and the PP terms to 0, this is 0, and you will only have these contributions for these two terms. So then finally, the case of the chiral medium. For the chiral medium here in blue, you see again that there's no play of the polarization because it's only the moduli. And also here, but that was expected because you are, again, it's chiral, so you are not having a real magnetic dipole moment here because you are only playing with the electric dipole. So that was expected. And also there's a very important principle in electrodynamics or in solid state physics, which is called the Curie's principle. Curie's principle establishes that in order to prove symmetries properties of a crystal, the crystal and the source must share the same symmetries. And in this case, we are proving chirality, let's say, with only an electric dipole. Therefore, these sources are chiral. In front of a chiral crystal, there's no way to expect such a response. That's the reason that we found no terms with time reversal symmetry. And for the velocity term, it's otherwise. So here it is again, here this optical, chiral optical strength thing. And here are the crossed Fresnel coefficients. I have to say that here the these Fresnel coefficients for the chiral medium are not the same as in the topological insulators, but are quite similar. Again, here we found problems with the perpendicular motion. So similar for the decay rate, again, it's quite similar. Again, it's important to stress that we recover fine results for the limit cases. Again, we can send the SS and the PP coefficients to 0 in order to see what will happen with a chiral mirror, with a perfectly chiral mirror, and therefore this will be 0. And for it's an ideal media, we know, but it's only to extract more insight on what is happening here. So therefore, in that case, for the perfectly chiral mirror, these terms will be 1 and -1 depending on the polarization, but you see that this is directly different from 0 in comparison with this. Similar situation for this one, and again the problem with the perpendicular motion. But then I'll come to my conclusion. So the formalism of macroscopic QED can be extended to this kind of non-reciprocal media, and we are able to obtain spectroscopical quantities, and we applied these results for concrete materials. So at least I reported to you, or I presented here, only for these real media, so the 3D topological insulators, which exist in laboratory. Magnetoelectrics also exist in nature, mainly. And in this way, we could read the conditions that the atoms should fulfill to observe new effects. In this case, it's because you need explicitly polarizations in order to prove these spectroscopical quantities. If you put explicitly here in this capital B that I showed you linear polarizations, then this is directly 0 because there are parallel. So that means that you need circular or elliptical polarizations in order to prove that. So, and also that is congruent with time reversal symmetry breaking. So I will stress again, there's a problem with the perpendicular motion that deserves more attention to solve it. And that's connected with one quote that Carsten told that in his talk, that there are problems on how to take limits in these kind of problems. The outlook, the role of the temperature for this kind of probe, for the friction, obviously I omitted, but we have also formulas for the force. Also study the force, it's necessary. This project that we are developing with a PhD student, which is the heat transfer between non-reciprocal media, which is depicted in this picture, and from the point of view of the field, and only from the classical point of view, we are also studying the Vavilov-Cherenkov, which is the classical analog to the quantum friction, but with a standard classical classical electrodynamics, but with considering in a correct way how the magnetoelectric coupling will modify the radiation. So with that, my acknowledgements. So, and finally, Stefan told me that I should provide this thing, that there's a PhD position. If you know someone that could be interested, please send an email to Stefan, and that's all. Thank you very much.